Most people see a cargo ship and assume the story is simple. Cargo goes in, engines run, and the ship moves across the ocean. But hidden beneath the decks of this vessel is an entirely different machine. This ship is not powered by a traditional diesel engine. Instead, it operates as a floating electrical power plant built around hydrogen, fuel cells, advanced energy management systems, batteries, electric motors, and a highly efficient propulsion system. Today, we're going to follow the complete energy journey from hydrogen storage all the way to the propeller and discover how a hydrogen-powered ship actually works. Inside a hydrogen-powered ship, what you're looking at is the complete architecture of a hydrogen-powered vessel. At the front of the ship are the bridge, navigation systems, passenger spaces, and crew accommodations. In the center sits the cargo area where revenue-generating freight is transported, but the real story is happening toward the rear of the vessel. Notice the dedicated hydrogen compartment containing large storage tanks. Next to it are the energy conversion systems and propulsion equipment. Unlike conventional ships where a giant diesel engine dominates the machinery space, this vessel relies on an electrical architecture. Hydrogen is stored on board, converted into electricity, managed through power electronics, delivered to electric motors, and finally transformed into thrust. The lower section of the slide shows the entire energy sequence. Hydrogen is stored, converted into electricity, managed electronically, delivered to propulsion equipment, and ultimately transformed into movement. This overview provides the roadmap for everything we're about to explore. How does this ship actually operate? Now the ship has been simplified so we can clearly see the complete energy pathway. A glowing hydrogen blue flow path traces the journey from the storage tanks all the way to the propeller. The process begins with hydrogen storage. Those tanks contain the energy needed for the voyage. The hydrogen then moves into the fuel cell system, where electrical power is generated. Next, the electricity passes through power electronics that regulate voltage, frequency, protection, and distribution. From there, electricity flows into the propulsion motor. The motor converts electrical energy into rotational force. Finally, the rotating shaft turns the propeller, creating thrust and moving the vessel through the water. Notice that every major system is connected by a single energy pathway. This is what makes a hydrogen ship fundamentally different from a conventional ship. Instead of relying on combustion to directly produce motion, it uses electricity as the central energy carrier throughout the vessel. Inside the hydrogen storage room, we now move into one of the most important compartments on board, the hydrogen storage room. Standing between these massive tanks, we can immediately see the scale of the storage system. The tanks occupy a significant amount of space because hydrogen requires more volume than conventional marine fuels. This is one of the major engineering challenges of hydrogen-powered transportation. Along the sides of the room are stainless steel pipelines, pressure management equipment, isolation valves, and monitoring systems. Above us, ventilation systems continuously move air through the compartment. Every tank is connected to safety systems designed to monitor pressure, temperature, and hydrogen concentration. If abnormal conditions occur, individual tanks can be isolated automatically. Leak detection systems continuously scan the environment, while ventilation prevents any accumulation of hydrogen. What we're seeing here is not simply fuel storage. It's a highly engineered energy vault designed to safely contain enormous amounts of stored energy while protecting the ship, crew, and cargo throughout the voyage. How the fuel cells generate electricity. This room is the heart of the ship. In front of us are rows of PEM fuel cell stacks. The slide clearly shows hydrogen entering from one side and oxygen entering from the other. Inside the stacks, an electrochemical reaction takes place. Unlike a diesel engine, nothing is burned. There is no combustion chamber, no explosion, and no piston movement. Instead, hydrogen and oxygen react electrochemically to produce electricity. The outputs shown on the right side tell the story. Electricity leaves the stack and travels deeper into the ship. Water is produced as a byproduct. Heat is also generated and must be removed through cooling systems. The fuel cell stacks are made up of thousands of individual cells working together to generate reliable electrical power. This is the moment where stored hydrogen energy begins its transformation into usable electrical energy. Without this room, the entire vessel would simply be carrying hydrogen. This is where the voyage truly begins. The ship's electrical brain. The next stop in the energy journey looks more like a data center than a traditional engine room. This space contains DC converters, inverters, switchgear, protection systems, and energy management computers. Every watt generated by the fuel cells passes through these systems before reaching propulsion equipment or onboard electrical loads. The DC converters regulate electrical output. The inverters prepare power for different ship systems. Switchgear routes electricity throughout the vessel. Protection systems continuously monitor for faults and abnormal operating conditions. At the center of the room are advanced energy management computers. These systems monitor performance in real time and constantly optimize how electricity is distributed. This is why modern hydrogen ships increasingly resemble electrical infrastructure rather than traditional mechanical machinery. The ship's performance depends not only on producing electricity, but also on managing it intelligently. This room functions as the vessel's electrical nervous system. The hidden battery system. Many people assume hydrogen ships run only on fuel cells. In reality, most modern designs include batteries as well. This compartment contains large lithium battery racks organized into dedicated storage systems. Alongside them are cooling systems, monitoring electronics, and emergency isolation equipment. Fuel cells perform best when operating at relatively stable output levels. Ships, however, experience constantly changing power demands. Maneuvering, acceleration, waves, cargo operations, and onboard loads all create fluctuations. The battery system helps absorb these fluctuations. During periods of high demand, batteries can provide additional power. During lower demand periods, they can store excess energy. The result is a hybrid architecture where fuel cells provide steady power while batteries stabilize the system. This improves efficiency, reduces equipment stress, enhances responsiveness, and increases overall reliability. In many ways, the battery system acts as the shock absorber of the ship's electrical infrastructure. The electric propulsion room. We have now reached one of the largest machines on board. The massive electric motor shown here dominates the propulsion room. The cutaway view reveals the major components that make the system work, including the stator, rotor, bearings, cooling systems, and shaft connection. Electricity enters the motor and creates rotating magnetic fields. These magnetic fields interact with the rotor, producing rotational force. That force is transferred directly into the propulsion shaft. One major advantage of electric motors is their ability to deliver maximum torque almost instantly. They also contain fewer moving parts than conventional marine engines, reducing maintenance requirements and improving reliability. Cooling systems maintain operating temperatures while precision bearings support the rotating assembly. This is the point where electrical energy becomes mechanical energy. Everything we've seen so far has been preparing for this moment. The energy is no longer just electricity, it has become motion. How the propeller moves the ship. Now we move beneath the vessel to the final destination of the entire energy journey. The propeller converts rotational force into forward motion. As the shaft spins, the blades push water backward. The reaction force pushes the ship forward. The slide highlights several important factors. Water flow patterns show how energy interacts with the surrounding ocean. Blade geometry determines efficiency. Cavitation control reduces energy losses and protects equipment. Even small improvements in propeller efficiency can produce enormous energy savings over long voyages. That's why marine engineers invest significant effort optimizing blade shapes, materials, and operating conditions. Notice the glowing blue energy path entering the shaft. This represents the final transfer of energy through the ship. Nearly every unit of energy generated on board ultimately reaches this point. This is where propulsion actually happens. The complete energy journey. Now we can finally see the complete picture. The entire vessel is displayed once again, but this time the full energy pathway is visible from beginning to end. Hydrogen tanks store the energy. Fuel cells generate electricity. Power electronics manage and distribute power. Batteries stabilize the system. Electric motors create rotation. Propellers generate thrust. The ship moves forward without combustion. Every system we've explored plays a specific role in this chain. Remove any one of them, and the journey stops. Together, they create a completely new approach to maritime transportation. What looks from the outside like a normal cargo vessel is actually a highly integrated electrical ecosystem hidden within the hull. And that may be the most important lesson of all. The future of shipping isn't simply about replacing diesel fuel with hydrogen. It's about redesigning the entire energy architecture of the ship itself. If you want to explore more hidden industrial systems like hydrogen ships, fuel cells, electrolyzers, hydrogen infrastructure, and the technologies shaping the future of clean energy, visit H2 Hub by Renee Energy, the resource platform built for developers, engineers, consultants, and investors who want to understand how these systems really work beyond the headlines.